Alright, so let's talk about this coordinate mapping business here. So the idea here is that I've got some, well, let's do a specific example. Suppose that I've got two vectors, so let's put them in, how many, well, it's 4 dimensions, how about 5 dimensions? Gotta make sure they're not 1, 2, 3, 4, 5. Gotta make sure they're linearly independent. Okay, and so suppose that I know that my vector x is drawn from the span of these two vectors. So since it's drawn from the span, I could solve for those. How about let's kind of work backwards maybe. Suppose I've got 3 times the first vector plus 2 times the second. Right, so we'll just take a second and figure those out. I'll pause while I work it out. Oh heck, we'll do it live. 3 plus 2 is 5. I think that's 6. That's the next one. 9 minus 2, then 7. Minus 3 plus 2, and then that's going to be a 2. Good. It doesn't really matter what it is. Okay. But notice here just a couple things. One is that I know, because I worked it out this way, that if I were to try to solve the matrix equation, right, if I were to try to solve that equation, I know what the solution is. C1 and C2 is 3, 2. Right, so that's my answer. Okay. And so notice, by the way, that even though I'm solving this equation and the matrix is not square, and furthermore, you've got these, when you do a row reduction, you're going to have lots of rows of zeros, right? And so in general, we might not expect this equation to have a solution, but in this case we do, because we said that x was in the span of these two vectors, and so we ended up getting a solution. And so the solution in this case is a 2-dimensional coordinate 3, 2. And so what we're saying here is that we can identify this point 5, 6, 7, minus 1, 2 with the point 3, 2. Right? And in fact, any vector x in the subspace H can be identified with its coordinate vector. And so you might be saying, well, so what? Well, this is a vector in R5, this is a vector in R2. So this is a low-dimensional representation. This is a low-dimensional representation to the vector x. Right, so x doesn't have to have 5 elements in it. X can be represented by 2 elements. And so you might imagine that in fact your data may be in a huge dimensional space, like 600,000 dimensional space, a million dimensional space. And you may be able to express that in a low dimensional coordinate, say 10 dimensions. Well, that's a very big reduction, and we're going to see how to do that. We're going to try to find like the best k-dimensional subspace within just a cloud of data in order to represent our data. I think I said that right. The best k-dimensional basis for a subspace of the data. Good. Okay, and so this is why it's so important to think about the coordinate mapping, because the coordinate mapping gives you, this is the coordinate mapping, or the output of the coordinate mapping. This is the coordinate mapping. This gives you the low dimensional representation, right? Good. All right. And so, by the way, can we work backwards? from the mapping. So given an x and h, we know how to find the coordinates. To find the coordinates, right, we have to solve the system of equations. Because oh gosh, it's going to be hard to go backwards. There actually is a better way to do this, and that is with a different basis. So if you have a choice, of bases, the best basis for a space, is one that is orthonormal. Do you remember that word? Ortho means that the vectors, the basis vectors, are orthogonal, and normal is the normal in the Calc 3 sense, which means that the length of each vector is equal to 1. Okay? Now why is that? Suppose that I've got v1 through vk are orthonormal in Rn. Then I can put them in a matrix U. I'll call it U. I think I called it B in the book. Oh, okay, we'll call it B. V1. I'm going to call it U in just a second, but we'll call it V for now. B is this. These are the columns of B, and this is n by k. Good. Now, what happens when we take our vector x and we try to write it as b times our coordinate vector? Is there a way you can solve for this? That's what we were asking before. Let's expand this out just to see what this actually looks like. This is c1 times v1 plus ck vk. Right, so I've expanded out this expression. Now what I'm going to do is I'm going to do a little trick, and it's kind of a common trick. I'm going to dot both sides with a vector vj, and where j is taken, vj is taken from the set. So j is going from 1 to k at some fixed value. Okay, so on the left you have x dot vj, and on the right you have c1 times v1 dot vj plus c2 v2 dot vj plus ck vk dot vj. And now something important comes into play. Our vectors are orthogonal to each other. Therefore, this is 0, this is 0, this is 0. Gosh, is there anything there? Yes, there is. Cj vj dot vj. But what is vj dot vj? You'll remember, maybe you remember, let's see if I can get back up here, that the magnitude of a vector, let's do it this way, the magnitude of a vector is, this is the magnitude squared, is v dot v, right? And so we said that if we have orthonormal vectors, this is equal to 1. And so therefore down here this quantity is just equal to 1. And so now what you see here is that we've just solved for Cj. The jth coordinate in our vector is just x dot vj. Now I should say that if the vectors are not if they're not normalized, then you would have the x dot vj divided by vj dot vj. Do you guys recognize this quantity from Calc 3 and linear algebra? Gosh, we've had 2 classes about that so far. And now we have a third. This is the scalar projection of x onto vj. Okay? And so if you want to project x onto Vj. If you want to take the orthogonal projection of x onto Vj, that is the scalar projection times, that's going to be Cj times Vj, or x dot Vj divided by Vj dot Vj times Vj. Okay, good. All right, and so what we're getting to here is that this equation actually can be simplified a lot, because now we know what the c's are, right? So in the case that we have an orthonormal basis, then you can write that x is equal to, v1 vk times our vector c, that's our coordinate vector with respect to b, right? And we know what this is now. This is the CJs, right? I'll use the normalized version. And so gosh darn it. Sorry about that. Oh gosh, we're running out of time. The coordinates of x with respect to b will show in the next video. Our matrix B transpose times x. Okay, good. I'm going to pause here since we're out of time, and in the next video we'll prove this statement. Did we finish both of the things that we talked about, that we said we were going to do at the beginning of this video? Coordinate mapping and how to compute coordinates. Okay, we just about finished it. Just got a bit more, and then yeah, we'll see what happens after that. Okay.